Okay guys, previously we've been looking at modeling exponential growth or decay using functions of the form y equals some a times b to the x, where previously we've seen that a represents some initial value and b represents some base or some growth or decay factor. And so what we're going to be doing is expanding that definition to include this one that you see above, but what we would call this one above is basically a simple model for exponential growth or decay. And I want you to see some similarities and differences. So very quickly here, let's talk about how these two functions right here and right here are related to one another and how they're also different. So looking at this down here, we've been saying that some amount of something at time x is given as the initial amount times some base to the power of x. Up here we're going to say that this a here is the new amount, or the amount at time t, where t, our time, is located over here. And so you can see that instead of x we're using the letter t, and instead of y we're using the letter a. In terms of other letter switches here, we're going to say that P is our principal amount, or the starting amount, and so still represents this A value here, except for we're using a capital P now to indicate this. And then the funny thing about B is that B is actually being written as either 1 plus or 1 minus R. And so what I want to do is talk about this R as being the rate of growth or decay. So the difference between our standard models, which is y equals ab to the x, and what we're doing now is that now we're going to be given some rate, and we're either going to have to add that rate onto 1 or take it off of 1. But we're going to have to write it in this way. And so let's take a look at how we can do this here. A few things before we get into doing that. Really quickly here, a few notes. We would say that this 1 plus r part, this is the part of our function known as the growth or the decay factor. So we still have this growth or decay factor, but just to be clear, if r is positive, then the function is going to exhibit growth. And so I do want to note that here. If we are adding on some rate, then we're going to be multiplying p by a number greater than 1. In other words, we're going to have growth here if our base is bigger than 1. And if r is negative, then we're going to be adding 1 to a negative r value, which means that this inner value is going to be less than 1, and the whole function is going to exhibit decay. And so this r, it all comes back to r being written as a percentage being positive or negative to tell us whether we're growing or decaying. So it says for this following situations, let's identify both the initial amount and growth or decay rate. Then we're going to use the model to write an equation that models the situation. Lastly, we're going to use our model to answer some questions. So for 26 here, we indicate that grandma gives you $2,000 upon getting your first real job to start a retirement fund, and the investment fund pays you at a rate of 4% annually. So to begin with, let's talk about our principal amount here. We're starting with $2,000, and that would be easy for us to go over here on this table and say at time 0, we're starting with 2,000 of something here. But as far as the rate is concerned, we see that we're given a 4% rate now. Here's the thing. We have to write the rate as a decimal. And so this means that we have to write this as 0.04, even if we're going to list it as 4% to the left. So this 0.04 is our rate. I'm going to say that this is growth, and the reason why is because it says that the fund pays you at a rate of 4% annually. You're not paying them. So with respect to our model, now we're using this model over here this time. We're going to write that the amount that I have at any given time is equal to the $2,000 I started with, but times 1, and in this case we're going to write plus 0.04, and this is to the t, or time. Now when we write a model, that means that we're not going to actually plug in a time value here. We're just going to leave time general, but we'd say this would represent any amount at any given time t, as long as I start with $2,000 and I'm growing at a rate of 4%. Now in terms of how I would rewrite this model, I will tell you that we always write it this way first, but then we rewrite the model in order to simplify this base in here if possible. And so I'm also going to call this a equals 2,000 times 1.04 to the t. And you can see that now all of a sudden this looks a lot more like that exponential function growth or decay model that we had been using previously. It's just that our base is 1.04. Now what would this mean about this $2,000 that I'm starting with? Well, it would mean that when I take it times 1.04, that's going to be 104% of what I started with. So when you go back and say, well, is this really growing at a rate of 4%? This is why we write it this way in the first place as 1 plus or the minus the rate, because let's put it this way, if I'm growing at a 4% rate, then I'm going to have 104% of what I started with later. So this 1 right here always kind of serves as kind of like saying this is 100% of what you have, plus or minus some rate of growth or decay. Okay, so using our model, we're going to find the amount of money in the retirement after 10 years after the first deposit here. It just means that we just need to pick up our calculator here, and we can do it one of two ways. I'll do it the first way here. 1 plus 0.04 would be what I'll write on the inside this time. We'll take this to the, I suppose, 10 years later, so the 10th power. We could get this answer right here. At the same time, I could have written 2,000 times, in parentheses, 1.04 to the power of 10 years later. but I would have gotten the same value. So 10 years later, we're going to have about $2,960.49. So 2960.49, and this is in dollars after 10 years. Now, in terms of 30 years later, let's get our calculator back on. What I want you to be doing is hitting second enter, and we can just go back and change our amount of times of compounding to 30. In this case, we get 6486.80. 6486.80. So we can see that this is growing here, and I do want to take the time to put this in our table. So 2960.49, and then we had here 6486.80. So now the last question I want to kind of address is this. Well, then using our model, let's estimate the amount of time we need to have pass until the account has at least $10,000 in it. Now, in terms of the model, we were given this up here, amount equals 2,000. We wrote this on our own, times 1.04 to the t. But the thing here is this. I'm giving you an amount this time and asking you to go plug it in for the amount here. And so what we're really trying to find out is, if the amount is $10,000, then what must this time be? And so this is a little bit harder to do, especially if we haven't talked about logarithms or solving exponential equations. And so from here, what I'm going to ask you to really do is kind of go back up and, using your model and your calculator, just kind of start guessing and checking until you can get it to be really close to $10,000. And so we know it has to be at least 30 because we were only at about 6,500-ish dollars there. But if we hit second enter and say maybe go big or go home, we say 40. Let's go out to 40 years. I'd see that 40 years still hasn't gotten to $10,000. So I know that if I were to go 50, I have a feeling that if I were to go 50, it would be way too much. And so what we're kind of trying to do is narrow it down. Well, if it's bigger than 40 but less than 50, maybe what we do is we kind of go halfway, 45. So 45 is clearly too big here. We'll go to the 40. How about 43? Ooh, this is really close to 10,000, and I'll go 42. We'll go back and change this to a 42. I think I've nailed it here. Nope, still haven't. We'll go back and change it to a 41. We're trying to get a number that comes out to be under 10,000, a number that's over 10,000. So when we have here, I notice that at 41 years later, I'm going to be a shade under 10,000, but at 42 years later, I'm going to be well over 10,000. And so I'm going to say between 41 and 42 years would be my answer here. And these are the kind of answers that I'm going to be looking for up front. Okay, so between 41 and 42 years. Okay, so now what I want to do is kind of look at another situation in terms of decay. We'll put this one together a little bit faster this time. It says you purchased a new car for 30 grand, and the particular value of this car decays at a 20% rate each year, which is actually pretty accurate. So we're going to say our principal amount is $30,000, but our rate here is 20%, and what I'm going to write is that this is a negative 20%. So in other words, negative 0.20 here, this is going to represent a situation where this is decay, the value of my car going down. So in terms of writing our model, we say A equals my principal amount. So we're going to start with this 30,000, and this time we're going to have a 1 minus 0.20. We're going to take off 20% from the whole, and this is to the t. So here's our model. Remember that once you get your initial model written, that we always want to rewrite it so that our base is a little bit cleaner. So in this case, when I rewrite 1 minus 0.20, I'm going to say, well, that's technically 0.80. And another way to look at this is we're only keeping 80% of the value of this car every year. And that's why we're multiplying by 0.80. So having this together, we're going to find the value of our car over the first 5 years. This is just calculator work. And so we'll go ahead and turn this on. As a matter of fact, we'll clear this out. We'll say 30,000 times, in parentheses, 0.8 or 0.80 to the 1. Now you're going to notice I did 1 first, and I get 24,000. The reason why I didn't do 0 is because we know the initial value was 30,000 to begin with. And so turn my calculator back on, we can go ahead and now get 2 years, 3 years, and while I'm at it, I'm going to go ahead and get 4 years. I can fit 3 values at a time on this calculator. So 19,200 was at 2 years is the value of my car. That's kind of depressing. 15,360 is at 3 years. 15,360. 4 years, we got 12,288. So 12288. And then 5 years later, just to make your day even worse, this is what your $30,000 car would be worth 5 years later, decaying at this rate. $9,830.40. $9,830.40. And so the idea here is, does the car decay in value more rapidly between 0 to 3 years or 2 to 5 years? The idea would be, if we were to look at the range of values between the 0th year and the 3rd year, which were these right here, we would get a difference of about, let's see, 30,000 minus 15,360. we would get exactly 14640. And so this is in dollars 14640. That's how much money we lost on the car in value over the first 3 years. But from the second year to the fifth year, that would be 19,200 minus 9830.40. And in this case, we also get a dollar amount. You're going to notice, though, it's going to be less of a change between those years than in the first 3 years. And the real question is, why does this happen? Why does it change so much in the first 3 years? And the reason why is because when you're finding 20% of a big number, that's a big number. But as our value of our car continues to go down, when you decay by a rate of 20%, 20% of a smaller number isn't going to change by as much. And so we get a 9369.6, 9369.6. But it only goes down about $9,000 over the second to fifth year, whereas it went down about almost 1.5 times as much in the first 3 years. So using this model, I want to do a similar thing we did last time. Estimate the amount of time it's going to have passed before it's worth $10,000. And the neat thing here is that we've already made a table sufficiently far enough out to see that it goes from above 10,000 to below 10,000 between years 4 and 5. So we're going to say between years 4 and 5. And as far as we're concerned right now, we just kind of want to narrow it down to that. Cheers.